Section 3.4, Newton's law of inertia. Newton's law of inertia states that an object at rest tends to remain at rest, and an object in motion tends to remain in motion unless there's a force that acts upon them. We usually call his first law of motion the law of inertia, and it's just restating what we were talking about with Galileo, that it doesn't take a force to keep an object moving. In fact, an object is going to keep moving unless a force acts on it. So if an object is at rest, it's going to stay at rest and only going to be moved if something happens to it. So you've all seen the example of the, pull the tablecloth out. All those objects are at rest. If you pull the tablecloth out, you can see that they all stay at rest, and that's an example of inertia. Also, objects in motion tend to remain in motion. If there's no other forces acting on them, they're going to keep going forever. Right now, the space station out in space, it keeps going. They don't have to keep firing the engines or anything. It just keeps going forever because there's no other force acting on it that's going to slow it down. Or, if you've seen like an air hockey table, you can see how, with very, very little friction, something like a hockey puck is going to move along for a long time on something like an air hockey table. So, objects continue to move by themselves unless something else acts on them. Forces are needed to overcome the friction that they have in order to get them in motion. And once they're moving, they're going to keep going in a straight line forever. If you were out in space and you threw a baseball, it would keep going forever until something else acted upon it. Maybe it got too close to another planet. But otherwise, it would just keep going forever and ever and ever. And here's a cute little picture. The dog takes off, sees the cat, or if it was the dog from Up, it would see a squirrel and take off and run. Or here's another one. Alright, so a force of gravity between the sun and its planets holds the planets in orbit around the sun. If that force of gravity suddenly disappeared, in what kind of path would the planets move? So if all of a sudden our sun disappeared, what would the Earth do? How would it travel? Think about that. Well, what would happen is they would all travel in a straight line at the same speed that they were going at. Alright, is it correct to say that the reason an object resists change and persists in its state of motion is that it has inertia? We don't know why objects persist in motion, but we call that property inertia. So, okay, section 3.5, mass. The more mass an object has, the greater its inertia, and the more force it takes to change its state of motion. The amount of matter in an object is known as the mass, and the more mass you have, the more inertia you have. So, in a sense, mass is really just measuring the amount of inertia that an object has. And an example, if you kick a can that's empty, it's going to go quite a bit. If you kick a can with sand, it's not going to move quite as far, and obviously that's going to hurt a little bit more when you do that. So, don't confuse mass and volume. Volume is simply the measure of space. Mass is more, we're talking about how many of the atoms and everything else in there. It's more about what's there, not necessarily how much space it takes up, how much volume, but the mass of it. So mass we're going to measure in kilograms. So for instance, which has more mass, a feather pillow or a common automobile battery? Well, think about it. Which one is harder to put in motion? Which one would be harder to kick and make it move across the room? Well, that's pretty simple. That's the battery. So even though the pillow is larger, has a bigger volume, it has a smaller mass. So mass also, like I said, is not weight. Don't be confused with that. It is proportional to weight, And weight is basically a measure of the pull of gravity on that object. And so the more mass you have, if you're on the Earth, the more mass you have, the more you're going to weigh. And if you have twice the mass, you'll weigh twice as much as the object that had half as much mass. However, the weight would change depending on where you're located. So if you're measuring your weight here on the Earth and then you go to the moon to measure it, you would find that it's different. Your mass, on the other hand, is never going to change. So mass stays the same no matter where it's at. Weight, on the other hand, varies depending on where it's located. It is kind of interesting to think about this, but it is just as hard to move a big rock with a lot of mass out in space as it is on the Earth. You still have to apply a lot of force to accelerate that object. And so despite the fact that it's weightless, it would still be hard for you to shake it up and down. It's not like it doesn't require any force to do that. So mass is the quantity of matter in an object, or we could call it the measure of inertia, or they say sometimes the laziness of an object. Weight is the force of gravity on an object. And like I said, they are proportional to each other. In this particular section here, they talk about how 1 kilogram weighs 10 newtons. Now that's a little bit of a round off. It actually is 9.8 newtons, but to make it simple, they use 10. So when we're talking about a kilogram of a mass of an object on the Earth, it would have a weight of 10 newtons. And a kilogram, just so to kind of put it in perspective, is about 2.2 pounds. So, you know, a pound is about 4.5 newtons, I believe, is what a pound is, something like that. So the SI unit of force is going to be the newton, and we make that a capital N. 1 newton is a little bit less than 1/4 of a pound. So if you know the mass of something in kilograms, all you have to do to convert it to newtons is multiply by 10. Technically it's 9.8, but for us in this book we will use 10. So if we take a look at this scale, we've got this kilogram of nails. It weighs 10 newtons. That's here on the Earth. If you went somewhere else, like to the moon, then that would probably, it'd still be a kilogram of nails, but the mass would be somewhere like 1.5 or 1.6 newtons instead of 10. All right, so think about this. Does a 2 kilogram bunch of bananas have twice as much inertia as a 1 kilogram loaf of bread? Does it have twice as much mass? Does it have twice as much volume? Twice as much weight when weighed at the same location? All right, so stop it for a second. Think of the answer. Write them down. And the answer is 2 kilograms of anything has twice the inertia, so it doesn't really matter what it is. In the same location, mass and weight are going to be proportional, so 2 kilograms of anything will weigh twice as much as 1 kilogram of anything else. And except for the volume, the answer to all the questions is yes. Bananas are much more dense than bread, so 2 kilograms of bananas would occupy less volume than 1 kilogram of bread. The moving Earth again. One of the things that they argued against Copernicus was because they figured out if Copernicus' his ideas were correct, that the Earth was moving around the sun, it would have to move at about 20 kilometers per second in order to do that. And their thinking was, well, what if we've got a bird, it's sitting in a tree, sees this worm down below, so it's going to drop down to go get the worm. In that 1 second that it takes the bird to fall, it's going to have been behind by about 20 kilometers. And they said, well, that can't be possibly true. So that's why the Earth isn't moving. Oh, 30 kilometers, sorry. So that was their idea, was that they can't do that. Now, if you think about things in terms of inertia, then this makes sense. Okay? If the Earth moves at 30 kilometers per second, so do the trees. The worm does. So does the air. So does the bird. Everything's moving that fast. And so as the bird drops down, it's still moving with the earth and with the air and all those things. Just like you can be in a car and you can play catch in a car, even though the car is moving at 55 miles per hour. It's not like if you throw the ball up in the air, it suddenly goes out the back window. That doesn't happen. Everything stays with you, at that time. So the earth does move, but so does the bird, so does the worm. So fortunately for the bird, it can catch the worm. So we were talking about this. I said about playing ball. Here's our person flipping a coin in an airplane, and everything stays the same because everything has inertia. All the particles, all the air particles in there have the same inertia or have inertia, so they're all moving. So everything stays the same. Now here's an interesting thing. There's a 3 million kilogram steel ball that hangs at the 87th floor of the tallest skyscraper in Taipei. And the reason they have that there is it helps to stabilize the building when there's an earthquake, because it is so much harder for that much mass to be moving that it's not going to move as much. Okay, so let's take a look at these questions. 2,000 years ago, people thought the earth did not move. One major reason for thinking that was that, what? Write down the answer, and if you need to, stop it while you're thinking about it, and we'll take a look at the answer. And the answer is A. Number 2, according to Aristotle and his followers over centuries, Earth was at the center of the universe. The first European to effectively challenge this notion was A. Copernicus. Galileo's conclusions about motion helped advance science because they were based on A. Experiments rather than philosophical discussions. If gravity between the sun and the earth suddenly vanished, Earth would continue moving in a B. Straight line. To say that a 1 kilogram of matter weighs 10 newtons is to say that 1 kilogram of matter D is attracted to the earth with 10 newtons of force. The earth moves about 30 kilometers per second relative to the sun, but when you jump forward in front of a wall, the wall doesn't slam into you at 30 kilometers per second. Good thing. A good explanation for that is C. Both you and the wall are moving at the same speed before, during, and after your jump.